Hey everyone, Mr. Fransky here. We're going to be talking about piecewise functions today. This is something that I've found students often struggle with, but really if you follow the procedures for graphing piecewise functions, it's really easy, especially if you know your parent functions really well. Excuse me. So, students will be able to graph and identify key points of piecewise defined functions. So, let's take a look. So some of the key vocabulary you're going to be looking at: domain, range, stuff we've been talking about, piecewise function, breakpoint. That's an important one that I don't know if other teachers call it that, but that's what I always call it. And then the domain, of course, of a piecewise function. So let's take a look here. So piecewise defined functions always look something like this. They have this weird bracket in the front, and they tell you what's happening at different pieces of the domain. So the domain for this guy, there's nothing I can't plug in. It's all real numbers. And what's happening is the reason it's called piecewise is because they're breaking the function into two pieces. So they're saying before 2, so here's 2. That's going to be a really important point. So here's x equals 2. Before 2 and including it, the function is following one rule. And then after 2, the function is following a different rule. That's really all there is to it. So the way that I do this is I always graph the breakpoint first. So you find the breakpoint, and you put it into both functions that meet at that breakpoint. And you might have one of them with an open circle and one of them with a closed circle. They can't both be closed because that would violate the rules of function. It wouldn't pass the vertical line test. So let's see what's happening here. So I'm going to plug 2 into both functions. So I plug 2 into this one. 2 plus 2 is 4. So at 2 I go 1, 2, 3, 4. You think that gets an open or a closed dot? It gets a closed one because it's got that equals on it. There we go. And then I plug into the other one. 7 minus 2 is 5. 1, 2, 3, 4, 5. That one gets an open circle because it's strictly greater than. So now we have to see what's going on with these things. So both of these are lines, right? The first one is, I'm going to write it as 1x plus 2. The second one, I'm going to write it as negative x plus 7, right? It's written a little bit different. It's a little sneaky, but it's not too bad. So the first one's 1x plus 2. So that's this line with a slope of 1. So before 2, everything before 2, it's going to be following that top rule. So it's going to look something like this. Now some of you might say, wait, you're drawing down. I thought the slope of that line was positive. Well, from left to right, it is. Look at this. From left to right, we're going uphill at a rate of 1. I just drew it backwards because it ends here. Now notice it also has that y-intercept of 2, which is exactly where it should be. Now the other line starts up at 2, and it's good for the rest of the time. It has a slope of negative 1. So I'm going to draw that one down to the right. That's all there is to draw in this piecewise function. Notice it never hits 7. Right? Some people really have a trouble with that. They're like, why doesn't it hit the y-intercept? Well, the answer is because it never gets there, right? It's only good beyond 2, so it never hits that point. Let's try another one. We have 3 pieces this time. So it looks like we have a breakpoint at 0, 1, 0 and 1, that's it. And I guess I should have said, really I only had one piece of the procedure here, and that's really all there is. So then all you do is just graph the functions in their respective domains. And that's all I did here. Domains. Okay, so all I did was to the left, I said, well, it follows this thing where we're climbing up. To the right, it's following this thing where it goes down. That's all there is to it. All right, so breakpoint at 0, breakpoint at 1. So I'm going to plug 0 into this function. When I plug 0 into x squared, I get 0. So that's going to have an open circle. When I plug 0 into e to the x, e to the 0 is 1. That's going to get a closed circle. It's possible that this isn't here at all. You could have 2 open circles. Right, that would be okay. But in this case, we have a closed, right, because it's less than or equal. So that gets a closed circle. And now, let's see here. If we plug 1 into e to the x, we get e. E is 2.7, so that's right about there. 2.71828, it goes forever, but it's about 2.7. And then what's this thing? My goodness. 1/2 x minus e plus 1 when x is greater than or equal to 1. I think I made a mistake on this one. That is not the function I wanted to graph. So I'm going to change it. I mixed up my x and my y. I wanted to graph the point 1e with a slope of 1/2. So let's see here if we can do that. A point 1e with a slope of 1/2. So what I should have done is y minus e is equal to 1/2 times x minus 1. And I wanted to solve for y. So y equals 1/2 times x minus 1 plus e. So notice I just mixed up the 1 and the e. So let's just fix that. So 1 there and e there. That's all there is to it. All right, so if I plug 1 in here, I get 0 plus e, which is e. Oh, that picks up right where I was. And some of you might have caught that should have been an open circle because it's strictly less than 1. So this actually fills in that point. Interesting. So let's see what's going on. So you have x squared before 0. That's a parabola, so it's going to look something like this. So we have the left side of a parabola, because that's what we have before 0. Then between 0 and 1, we have e to the x. That's an exponential, so it's going to be like curving upwards. And then beyond that, we have this line with a slope of 1/2. And there's your piecewise function. So notice that it actually was continuous at x equals 1. At 0, we still had that jump discontinuity, but at 1, it just continued on from its spot. Pretty cool. Now we're going to try the problems that you guys have on your gold sheet. So I want to give this a shot and see if we can come up with these piecewise functions. So if you want to try these on your own, feel free, and then you can come back and we can try them together. All right, let's graph this first one. So when x is less than -1, we have the function x minus 1. So I'm going to plug -1 into that function. I get -2. There we go, and it's an open circle because it's strictly less than. X minus 1 has a slope of +1, so it's going to look like that, right? We rise up to that point, and it starts way at -infinity, rising, rising, rising until we get to that point. Now notice this. We don't start up again until 0. So at 0, we're at 3, open circle. And we stay at 3 until 2. So at 2, we are still at 3, open circle again. There we go. That's a constant function there. Didn't want to drag that there. There we go. Now we're at x plus 2 when x is greater than or equal to 4. 1, 2, 3, 4. So we're at x plus 2. So 4 plus 2 is 6. 1, 2, 3, 4, 5, 6. So we get a solid dot there. Finally, we get a solid dot because we have that equal sign. And then we have a slope of +1. And that's all there is to it. Nice. So now the domain. Domain is interesting here. We're good from -infinity up until -1, not included because it's an open circle. And then 0 to 2. So I'm just saying where there is function here. And then closed bracket 4 to infinity. The range, -infinity up to -2. Right? And then we have a gap. I have to just do a bracket 3 now because it's got 3. And then looks like 6 to infinity. Closed 6 to infinity. Nice. Is it continuous? Heck no. Absolutely not. It's kind of weird to talk about this. Looks like we have a jump like between these two values. I don't even know how I would discuss the continuity here. It's definitely discontinuous. It's discontinuous like there's not even any function between -1 and 0 or between 2 and 4. But I would just say it's discontinuous. There's stuff weird going on here. We are increasing from -infinity to -1. Right? That's where we stop increasing. We are constant. We don't change from 0 to 2. And then we're increasing again. We can just add it here. 4 to infinity. Nice. Tricky problem, but not too bad. Let's try the next one. So pause this and try it again if you want to. So prior to 0, open circle there. We're going to have a parabola. Looks like that. And after 0, we have absolute value of x, so it's going to look like that. No solid dot at 0 because neither of them are equal. So the domain, everything except 0. -infinity is 0, union 0, infinity. Range, looks like we can't get 0, but we can go up as high as we want. Continuous, nope. We have a hole, or a removable discontinuity, it's called, right here at 0. Saying hole is just fine. That's a hole. It's not a jump because it stays at the same value, but it's plucked out of the graph. Now we have decreasing from -infinity to 0, and we are increasing 0 to infinity. Nice. All right, one more. No, I think we got a few more. Sorry. So let's give this a shot. Same deal. So we plug 1 in here. 1 minus 1 is 0, and it's greater than or equal, so it'll be solid. So root x minus 1. Sorry, I should put it at 1. So we haven't really learned this yet, but this is just the root function shifted to the right one. You could plug in some values for that to find out if you wanted to, but that's going to basically look something like that. So you could make a table for that if you needed to. And we were less than or equal to -1, so -1 minus 1 is -2. Solid dot there because it's less than or equal. X minus 1 is going to have a slope of +1. Hopefully you got something that looks something like that. So let's see here. Domain, -infinity to -1 included, and then 1 to infinity. Range, -infinity, we stop at -2 included, and then included 0 infinity for this part. Continuous, no, definitely not continuous. We jump from -1, -2 to 0, or sorry, 1, 0. So it's not continuous for sure. And we are increasing on the entire domain. I'm going to write that because there's never a point where we are constant or decreasing. Everywhere we have x values, the function is increasing. Cool. All right, let's give this one a shot. So less than or equal to -4, we're just at x, so plug in -4 there. We get -4, 1, 2, 3, 4, -1, 2, 3, 4 right there. So solid dot there. And then from -4 to 1, we're at -4. So we actually stay there until we get to 1, and we're having an open circle there. It would be open here, except it's closed by the previous function, so we can just leave it closed, right? Because this one gives us that value, but we stay there. Now, when x is greater than or equal to 1, we have 2x minus 3. So that gives us 2 minus 3 is -1. No, I was hoping we were going to have a continuous function. So we have a solid dot there. And now we got to fill in the rest of it. So we're at x before that, so it looks something like that. Slope of 1. And then 2x minus 3. So we have a rise over run of 2 here. So it's going to look something like that. And that's all there is to it. So domain, all real numbers, right? There's nothing that I can't plug in. Everything is covered. It's in 3 pieces, but everything's covered. Range, open -infinity to -4. And we can get that. Union, close bracket, -1 infinity. So we just miss the values between -4 and -1. We are not continuous. But we can actually talk about it this time. We have a jump at x equals 1. Increasing. We are increasing -infinity to -4. And we are constant from -4 to 1, and we are also increasing from 1 to infinity. Nice. All right. Take a look at the next one. I think we got one more. So let's graph this guy. X cubed less than or equal to 0. So that's going to look something like this, right? It's like the beginning of the lane change. Between 0 and 2, we're at 3, and it's open circles. Like that. And then we are x squared greater than or equal to 2. Interesting. So we come up to here, 1, 2, 3, 4, right here, open circle, and we're going to increase up forever. Sometimes you'll get things where you actually come back down. That's kind of weird. It's not always up, left, to right like this, but in this case it was on just about every graph. So another open circle there. There we go. So domain. Domain, we can't have 2. So -infinity to 2, union 2 infinity, and beyond. The range, -infinity to 0, closed. And then we can get 3. This is going to be a weird one. And we can also get open parentheses 4 to infinity. Just bottom to top. Continuous? No, not continuous. We have a jump at x equals 0 and x equals 2. Interval increasing, decreasing. They're increasing -infinity to 0. And also from 2 to infinity, open. And we are constant, 0 to 2. And that is that. Piecewise functions, not too bad. If you have more questions, let me know. Otherwise, I love you guys. That's why I'm here. Have an excellent day. See you guys soon.